Okay, so today we're looking at parametric equations, and that's where we take a pair of continuous functions where we define our ordered pair x, y in terms of a third variable. Okay, so we're going to take our normal horizontal move and vertical moves, and we're going to define them in terms of a third variable. That third variable is usually t, dealing with time. So that third variable is called our parameter, and that's where we get the name parametric equations from. Okay, so what it's going to look like is the ordered pair xy now becomes x with respect to t and y with respect to t. So our ordered pair xy is now going to look like this. X with respect to t and y with respect to t, because we have now defined that x and y in terms of another variable, generally t.
Do you have another parentheses? Yeah, what's going on?
Oh yeah, there I am missing a parentheses. Thank you. All right, so here's an example. A bug is walking along a curve. Okay, so everybody visualize the bug walking along the curve. At time 0, so at time 0, the bug is at the point 1, 2. Maybe it's being a little stubborn today, so let me plug it back up and see if that'll help.
Erase that.
No, you erased that thing over right there. Yeah.
All right, we are recording, guys. All right, so the bug is at the point 1, 2. Now, for every second that passes, the bug's horizontal position increases by 2. So we're talking about a horizontal change. Which variable would that affect, x or y? X. But its vertical position decreases. Let's do 3. All right, so let's investigate what we know. Okay? So we know that at time 0, the x position is what? 1. Okay? Because at time 0, the bug is at the point 1, 2. And we know the y position at time 0 is what? 2.
Oh, this is easy.
Okay? So when we do x with respect to time, it's that initial position plus the change with respect to time. Does that make sense?
Yes.
Okay? So what do you think y of t would be represented as?
2 minus 3t.
2 minus 3t. All right. So I'm going to steal these two and we're going to go to a new page. All right, so this is where we are. We have x of t represented by 1 plus 2t, and we have y of t represented by 2 minus 3t. So if we have this, then what curve is that bug walking on? All right, so we have three things going over here. We have time, which is our parameter. We have our horizontal position, and we have our vertical position. So at time 0, we said this was 1, 2, right? So let's see, as time changes, what this is going to look like. So 1 second later, what would x be? 3. And what would y be? -1. Okay? 2 seconds. What would x be? 5. What would y be? -4. 3 seconds. What would x be? 7. What would y be? -7. All right, so let's investigate this a little bit. What do you notice about this change? It went up 2. What about this one? Up 2. What about this one? Up 2. Where did that come from? The 2. Okay. What about this? -3, -3, -3. That came from? Yeah. All right, so let's graph this. Let's take a look at how this is going to play out. Okay, so that's not quite straight, is it? Okay, so we got this first piece of data, which is 1, 2. And that's at time 0, right?
Yes.
Our next data point is 3, -1. And that's at time 1, right? 1 second later. Our next data point is at 5, -4. And that's at t of 2, time 2. And our last data point, I'm going to have to stretch mine out a bit. I didn't make it long enough. Is 7, -7. Whoops. That should be right here. 1, 2, 3, 4, 5. There we go. And then the next one was at 7, -1, 2, 3. So down 3 more. So that's t of 3. All right, so we already determined what our parametric equation would look like. It's the x represented by 1 plus 2t. And my y is represented by 2 minus 3t. Okay, can we represent this curve anyway? Is it a curve?
I don't think so. Not doing.
This one is a line, isn't it? It is a line. So we can find a slope. It's the change in y over the change in x. Okay, so this is our parametric, but this is not. We determined that this is actually a line. And the change in the y over the change in the x's, we've already found the change in the y's, -3, the change in the x's, 2. And we'll pick a point. I'll give the one they started with, the point 1, 2. Okay, now this is our rectangular representation, and this is what we're used to. Okay, so this is with respect to our parameter, time. So our parametric is with respect to our parameter, our rectangular is not. Now these don't all turn out to be lines.
It'd be nice if it did.
Wouldn't it? So let's take a look at a parametric. So let's let x of t be t squared minus 2 and y of t be 3t. And we're going to do this for an interval. I'm going to go from -1 to 3. So first of all, let's see if we can figure out what this looks like. Okay, you think this one will be a curve? Most likely. All right, so our parameter is time. And let's see what this looks like. So we're doing it from -1 to +3. So I'm going to start at -1. 0, 1, 2, 3. So if I plug in -1, I get 1 minus 2 is -1. And I get -1 times 3 is -3. Okay, you complete the table for the other values. Okay, so did you get -2, 0? -1, 3? 2, 6? And 7, 9?
Yes.
All right, so let's sketch it. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. 1.
Oh, they're like, the first one's a graph or a curve.
Okay, there's our x. There's our y. So our first point is -1, -3. Okay, at time 0, we're right here at -2, 0. Then we're at -1, 3. Okay, so this was -1. This is +1. Do you see some symmetry going on there?
Yeah,
Okay, then we're at 2, 6. And then we're at 7, 9. Okay, so this path with respect to time is moving this way, right? Y'all see it? With respect to time. And then we're stopping right here. Does look like a sideways parabola. Good. Okay, so I like it. All right, now this sideways parabola isn't a complete sideways parabola, is it? It's restricted. It's restricted because of our parameter, time. Time was restricted, so our parabola is restricted. All right, so we have our parametric equation. Can we create a rectangular equation for our parabola? We kind of think it's going to be a sideways parabola. Do you guys remember how the equation for a sideways parabola is? X equals. So we're probably going to end up with an x equals. What happens to the y's? The y's are squared, and they're on the other side, right? Okay, so let's take what we do have. X equals t squared minus 2, y equals 3t. Do you see that if I solve y, well, if I solve for t here, I get y divided by 3 equals t. What can I do with this value of t now? I can plug it in. Okay, and when I plug it in, I get y over 3 squared minus 2. And guess what that is? That's the rectangular equation.
Wait, so I'm not getting that part.
Okay, so our goal was to eliminate t.
Oh.
Now, yeah.
It's divided by. Okay, I see.
Yeah, our goal is to eliminate t. And in this case, because we had some prior knowledge of what this equation should look like, we knew we wanted it to be an x equals and we wanted t to go away. So we took the second equation, solved for t, and substituted in. Okay? All right. So, let's work on eliminating that parameter. Like we just did. Okay, so if we had a parametric equation, let's do a fun one. So x this time is going to equal e to the t, which would be scary, but we know e is just a number, so it's not scary. And let's go ahead and make y something more fun.
E is just the. Oh wait, like the actual value of E.
All right, now we're going to do this for values of t that are greater than 0. Now looking at these two, I see that my x only has one t in it. Is it easy to solve for t when there's only one? Yes. So how can we solve for t if t is an exponent? What do we have to use? Natural log. I like it.
Oh my gosh, this is so great. I love logs.
All right, so we're going to take the natural log. And when we take the natural log of both sides, it ends up looking like this. And this exponent comes out in front, right? And becomes multiplication. Now, the fabulous thing about taking the natural log in base e is the natural log of e is 1. So we've solved for t. The natural log of x is t. So, plug it in. Natural log of x, natural log of x, and that eliminates the parameter. Actually, I'm going to put this in parentheses so you don't think it's the natural log of x plus 1. It's the natural log of x plus 1. All right. Last example. Trig. All right, so we're going to define this over the interval from 0 to 2 pi. All right, this is cool. You're going to like this in the end. Okay, we want to eliminate t.
Are we going to use our like trig functions, identities, or whatever?
Yeah,
Oh, nice. So do
we don't have anything with just sine and cosine, do we?
Can we square them?
We can square them. Love it. That is exactly what we do.
I'm going to go to the next test and like you should have squared.
All right, so let's square it. Okay, so when we square it, we get x squared equals 9 cosine squared t. Y squared equals, whoops, there should be a 3 right here, folks. I left the 3 out of the original equation. My fault. So this is 9 sine squared t. All right. Now, because y squared is equal to 9 sine squared t,
Oh, it's 9.
I'm going to add y squared to this side of this equation. But to keep it balanced, I'm going to add an equivalent value, 9 sine squared t, to the other. Do you see that I added the same value to either side of this first equation?
X plus y equals 9. Or x squared plus y equals 9, right?
You are so right.
Aaron, like, good.
She just sees it. She just sees it.
I have a vision. Y squared 9, and then so.
Okay, so she saw it. Because when we factor that common factor out of 9, cosine squared t plus sine squared t equals what? 1. And so what we're left with is x squared plus y squared equals 9. Think conics, guys. What is that? That's a circle. Okay? All right. So, we are doing page 530, 1 through 26. Let me see if I printed those out. I am sending them to the printer right now.